Okay, so now we're going to get into finding the extrema of a function of two variables. That's the book's word for maximum and minimum points, right? Maximum and minimum values of a function. So we'll consider a function of two variables, z as a function of x and y, on a closed and bounded region R, right? So a closed and bounded region just means, closed means it includes its boundary, right? And bounded just means it doesn't go on forever. So it can't be, for example, the entire xy plane. Okay, so yeah, let's suppose that closed and bounded region is just, could be a rectangle, right? Something like this. Right, so this is my region R. And right, if it's just a portion of the xy plane. So it doesn't have to be the xy plane exactly. So let's say this is the x-axis, this is the y-axis, right? And then above that region, you have some surface, right? Okay, sitting above that region of the plane, right? So as long as f is a continuous function, right, you're guaranteed to have the maximum. That's going to be the highest point, say right here. It doesn't, right, so let's say right here is the highest point, right? So if you look below it, on that region R of the xy plane, you have your x-coordinate is c and your y-coordinate is d. So the maximum value, right, is, let's say, z1, and it's just going to be f of c of d, c and d, right? But you also might have the lowest value. The lowest value, let's say, is, no, I kind of drew this funny, but let's say it's way over here, right? So sitting above the xy plane. So suppose my region R extended all the way to here, right? So this point right here would be your x equals a, y equals b, and then the minimum value here, if I can abbreviate, minimum value, right, is just, say, z0, which is f of a and b. Okay, so you have the highest point and you have the lowest point, right? So that's your maximum and minimum, respectively, right? And remember, these are absolute maximum and minimum points, right? It's the highest point over the region R and the lowest point over the region R. Right, and keep in mind that not all surfaces are guaranteed to have a maximum or a minimum. Right, but in this picture, we get a maximum here, we get a minimum down here. Right, so highest point and lowest point, right? In terms of z, right, we're measuring the elevation z above the xy plane. So the largest z value is this one, the lowest z value is this one. Got it? Right, and it can occur at more than one point, right? So maybe way over here, at this point, the z-coordinate is the same as it is over here. So that'll give you a different a and b, but the same z. Right, so you've done this all before, of course, with a function of one variable. So it's just a little more complicated when you have a function of two variables. But it's the same idea, right? Same idea. You have the lowest point, right, and then the highest point. Makes sense? Right. And I think I just mentioned the extreme value theorem. So let's do that. The extreme value theorem just states that if you have a continuous function, right, of x and y on a closed and bounded region, then that guarantees, right, that's a guarantee that you have both a minimum value and a maximum value. That is, there is at least one point, right, say AB, where you have the minimum value. And there is at least one point, well, it could be the same point, but not likely. It'll be a different point, C and D, where you have a maximum value. Okay, so yeah, the function has to be continuous, and I drew a nice continuous surface up here, right? So this surface, z, oops, that's a little too dark, right? Z as a function of x and y, right? I drew it as a continuous function. Right. Certainly if it's differentiable, it has to be continuous. But even if it's not differentiable, you can still have a maximum or minimum. It just might not look like a nice surface, that's all. Not that my surface is nice. It's kind of wiggly, right? So it has these contours here, right? So not a nice surface, but one that it is continuous, right? So, okay, and that's the extreme value theorem. Very similar to what it was in Calc 1. Okay, so I'm getting this out of the book too. I guess I'm getting tired of writing, so I'm just using the book's definition here. We have a function f defined on a region R, right? It doesn't have to be a closed and bounded region at this point, although it certainly could be, containing a point x0, y0, right? So the function f has a relative minimum. We'll do the minimum first. Relative minimum at that point if, well, the z values of the function are greater than or equal to the z value at x0, y0, right? So we think of a relative minimum as a valley. So think of like a paraboloid, like a little bowl here, right? This point here, if this is your xy plane, right below it, this point here would be your x0, y0. Right? And the idea is if I pick any other point, even one that's nearby, say x and y, when I go up to the surface, right, that z value up here, z, which is a function of x and y, right, that z will be bigger than or equal to this z down here, right? This would be the lowest z. So you can call it z0, f of x0, y0, right? So this would be a relative minimum, right? Why relative? Because it's only relative to points on the region R, right? In other words, nearby, right? So who knows what happens, what the surface does elsewhere. This surface could come up and come back down, and you have a really weird surface. So you do have points lower than z0, but not nearby, not locally, right? Yeah, so what we call a relative minimum, some books also call a local minimum. Same thing, right? So I'll try to use relative minimum, but if I ever use the word local minimum, yeah, I mean the same thing, right? And then for the maximum, it's the same thing except the opposite. Now you have a peak instead of a valley. So think of a little hill, little molehill here, and then your maximum, right? Here's your xy plane below it. Right below it, you have your x0, y0. But now, the z0, f of x0, y0, is the highest point around. So if I pick any other point nearby, right, not too far away, say xy, and I go up to the surface, that z value will be lower than z0, z0, right? So yes, this z here, f of xy, will be less than f of x0, y0. Or at least not bigger than. So it could be equal to, but not bigger than, right? So that's the idea. Right up here, the z will be bigger than or equal to f of x0, y0. Okay. So again, right, so we get a relative maximum or a local maximum. Okay, so again, nothing new, right? You did this all in your Calc 1 days, where you just have a curve. Instead of a surface, you have something like this, right? Right. And we would say that right here at the top, this is a local or relative maximum. And this down here, the valley, would be a relative minimum. Even though, right, it's not the lowest point around, if you go far enough away, there are points lower than this, but not nearby, right? You have to go far away. Right? Likewise, there are points, say this point up here, that's higher than this than this point over here. But again, if you're only looking nearby, if you're only looking in a small neighborhood, right, then this is the highest point, right? And if you're looking in a small neighborhood, this is the lowest point. Okay, so that's what we mean by relative minimum, relative maximum, or local minimum, local maximum. Okay. Okay, now we come to the definition of a critical point, right? So a critical point is it's a point, right? So in your Calc 1 days, remember we called these critical numbers, right? Right? I hope you're, I tried to call them critical numbers rather than critical points, right? So yeah, in Calc 1, when you have a function of one variable, you have a critical number, right? And it's basically where the derivative is either 0, so here's your critical number, right? Or where the derivative does not exist. Right? So like if it comes to a corner or a cusp. Okay. So, right, so same idea, but now we have a critical point, right? So here's your xy plane, right? And you have your point x0, y0. We say that that is a critical point if, so there's two possibilities here. Let's just look at the first possibility. Right, the first one is that the partial derivative, both partial derivatives, the x partial derivative and the y partial derivative are 0. Right, so that's going to happen when you have a surface that roughly looks like this. It's got to be a little bit better than that. Yep. So a nice smooth surface, like a hill again, where if you go up to the surface at this point, the partial derivatives are 0. What does that mean? It means that if I draw the tangent plane, I should say, it's going to be horizontal at that point, right? So remember the gradient will be pointing upward. I'm sorry, the gradient of capital F, right? The gradient of little f will be 0. So the gradient at this point here is just going to be the 0 vector. Right. In fact, that means the same thing, right? So I would have phrased it the following way, right? That x0, y0 is a critical point if, when you take the gradient and you plug in the x0 and y0, you get the 0 vector. Okay. So that's just saying that both partial derivatives are equal to 0, because remember what the gradient is. The gradient is just the vector with components, x partial and y partial. Again, plugging in the actual point here. Okay, so yeah, that just means that the tangent plane will be horizontal, right? And of course that can happen at a relative maximum. It can also happen at a relative minimum down here, right? Or if you look at it this way, the tangent plane is horizontal, right? So that's one possibility, right? The second possibility, which I'll do here, again, you have your xy plane, you have your critical point x0, y0, and what makes it a critical point is that either the gradient is 0 or the gradient does not exist, right? In other words, there is no gradient vector here. Does not exist, right? And what that could mean in terms of the partial derivatives, right? It could mean that either the x partial derivative could be 0 or the y partial derivative could be 0. They don't both have to be 0, although if they're both 0, then that still qualifies. It's still a critical point. So when does that happen, right? So that happens if your surface, right? Think of a cone, right? A cone will not be differentiable at the vertex, right? At this point here, there is no tangent plane. So, yeah, sorry, no tangent plane at the bottom there. So that means the gradient will not exist. In fact, both partial derivatives will not exist, right? Oh, I'm sorry, not equal to 0. Oh, I got to change that, right? So not equal to 0, I mean, does not exist. So either partial derivative will not exist. Sorry, because yeah, if they're both equal to 0, you get a critical point. If either one of them does not exist, you also get a critical point. Okay, and as a practical matter, we're not going to see this very much, right? I mean, yes, we've seen cones before, right? And if your surface has a ridge, like let's say something like this, where you have kind of a peak here like this, right? Then all of these points right here could be critical points. But luckily, we're not going to see that very much. That doesn't come up all that often. So number 2 is something you have to be aware of, that, right, this could give you a critical point as well. However, for, like, I would say 95% of the homework, your critical points come from where the gradient equals 0. In other words, where both partial derivatives equal 0. But, you know, once in a while you'll see one where both partial derivatives fail to exist. Or either partial derivative fails to exist. And that gives you a critical point as well. Okay, so I hope that explains the definition of a critical point. Right, so why are critical points important? Well, they lead us to relative maximum or minimums. Right, so this theorem here just says that, right, a relative maximum or minimum point, right? So that's not just the x0, y0, but also the z0. Right? Z0 would be the maximum or minimum value. So a relative maximum or minimum point must occur at a critical point. In this case, x0, y0 is your critical point, right? Remember, it does not include the z0, right? That's not the critical point. The critical point is in the xy plane. Sorry, y0. And then when you look at the surface, right, the surface might have a maximum or a minimum there. So when you go up to the surface, the peak of that surface, the highest point, gives you your x0, y0, z0. Z0 being this height, this difference, the difference between the 2 points, right? Okay? Yeah. So, right, you can't have a maximum, you can't be a minimum or a maximum and not be a critical point. Okay. But don't get this backwards, right? This does not say that if, right, a critical point gives you a maximum or minimum. In fact, that's not necessarily true. Right? So a critical point, x0, y0, right, does not mean that the z0 is a relative maximum or minimum. Right? Or it does not mean that this point, sorry, my z's are sloppy. There we go, z0. This does not mean that this is a relative maximum or minimum. Right. That does not have to be the case. So just because you have a critical point does not mean you have a maximum or minimum. However, if you have a maximum or minimum, then that has to be at a critical point. Okay? Yeah, just to bring it back to Calc 1, right? If you have a critical number, right, if x0 is a critical number, that does not mean that, right, that this is a maximum or minimum. Right? It could be, right? So you can have if this is your critical number, it could be because you have a maximum, or, you know, it could be a point of where it's not differentiable, right? Or it could be a minimum. So something like a valley like this, or, oops, I missed it, or a cusp like this, right? So yeah, the idea is you find your critical numbers hoping to find a relative maximum, right, or a relative minimum, but not necessarily, right? So if this is your critical number, the graph could look like this. It could level off and then go back up. So at this point here, we would not say that this is a maximum because there are points higher than that. And it's not a minimum because there are points lower than that nearby. So this is neither a maximum nor a minimum. Right? Although the x0 is a critical number because the derivative is 0 there, right? Remember, the tangent line is horizontal. So yeah, it's a little bit more difficult to draw, but you can imagine a tangent plane being horizontal, right? But not necessarily being at a maximum or minimum. So yeah, just take this graph and just make it a three-dimensional graph, right? So a little bit harder to visualize, but it's the same idea here, right? So yeah, so critical points, right, could be a maximum or minimum. And in fact, that's where you look for them, right? If you're looking for a relative maximum or minimum, you got to find the critical points first, because that's the only places you'll find a maximum or minimum is at a critical point. But when you find the critical points, you have to check that you have an actual maximum or minimum. Just because you have a critical point, first of all, it doesn't tell you whether it's a maximum or a minimum. It could be a maximum, it could be a minimum, right? But it could be neither. It could be neither, just like in this picture here, right? So just be aware of that. Okay, so that's this theorem that tells you maximum or minimum points occur at critical points, but not vice versa. Okay, so we're going to start with an easy example, and we just want to find the critical points of the function f of xy equals x squared minus 2y squared. Okay, right, so how do we find critical points? Right, well, right, remember the two possibilities. One is that both partial derivatives are 0, and the y partial is 0. Or the other possibility is that either partial derivative does not exist. So this partial derivative does not exist, or the y partial does not exist. It could be both, but it does not exist. I'm making that same mistake again. Okay, so that's the definition of a critical point, right? So when I think of how do you find critical points, I automatically just go to the derivative, right? In this case, the derivative is just the gradient. So the gradient is, again, the partial derivative with respect to x is 2x, and the partial derivative with respect to y is negative 4y. So where is the gradient equal to 0? And by 0, I mean the 0 vector. Well, you get two equations, right? Sorry, that's supposed to be a 4, right? So you solve those equations, and you just get x equals 0 and y equals 0. So there you go. 0, 0 is a critical point. In fact, it's the only one, right? There's only one solution to this system of equations. So that has to be the critical point, right? And yeah, you can check, right? As a way to check, plug that number into the gradient, and you get 0, 0. You get the 0 vector, right? So that's what makes it a critical point. Okay, here's another hopefully easy example. Find the critical points of the function. Now I wrote it z equals the square root of x squared plus y squared, but we can easily change that to f as a function of x and y. And I'm going to write it this way, right? So it's going to be x squared plus y squared to the power 1/2. Right? And now just take the gradient. So for the x partial derivative, when you take the derivative, you get 1/2 times x squared plus y squared to the negative 1/2 times 2x, right? So I think that's going to give you x divided by the square root of x squared plus y squared, because I think the 2's cancel. And then the same thing for y. The y component is y over the square root of x squared plus y squared. Okay, so where's this equal 0? Well, be careful. If you're thinking if x is 0, right, the numerator 0, notice the denominator is also 0. So the fact is, this is never going to be the 0 vector, right? So yeah. Right, if you try to do the same thing we did in the last example, you set this equal to 0, sure, that gives you x equals 0. If you set the second component equal to 0, right, then that gives you y equals 0. However, as a check, if you plugged in 0, 0 here, you don't get anything. You get 0 divided by 0. So this does not exist. However, that's the second condition, right? If the gradient does not exist, then you get a critical point. So 0, 0 is a critical point, but not because the gradient is 0, not because both partial derivatives are 0. In fact, both partial derivatives fail to exist. But that's what makes it a critical point. Right. In fact, this is just the cone we talked about earlier, right? This is a cone. So 0, 0 happens to be the bottom of the cone, right? So this is the point, well, 0, 0, 0 actually. Yeah, so there will be no tangent plane there. There's no gradient here, right? So the gradient does not exist. And yet, we still want to consider it to be a critical point. Why do we want it to be a critical point? Well, remember what we do with critical points. We look for relative maximums or minimums. And based on this picture here, this certainly looks like a relative minimum, a local minimum, right? It's the lowest point. In fact, it's also an absolute minimum, right? Because it is the lowest point, right? But in any event, it's also considered a relative minimum, right? Even though you don't have the nice smoothness that you did in the first example, right? So if you have a paraboloid, you have a minimum here because it's nice and smooth, right? Or if it's an upside down paraboloid, you have a maximum where it's nice and smooth. But it doesn't have to be smooth, right? Sorry, it can also come to a corner or a cusp like this and still be a relative maximum or relative minimum. Okay, so yeah, this is the cone that I mentioned earlier, and this is the case where you have a critical point because either partial derivative fails to exist. Okay, so now we can actually talk about how to find the relative maximum and minimum points, right? We're looking for the relative maximum points, those are the peaks, or the relative minimum points, those are the valleys, right? So, right, step one, find the critical points, right? Because when you have a maximum or minimum point, they only occur at the critical points. So you might as well look there. So when you're finding the critical points, you're finding essentially possible maximum or minimum points. But just because it's a critical point doesn't mean it has to be a maximum. It doesn't mean it has to be a minimum, right? It could be neither. But that's where we look. We look at the critical points. So find the critical points, right? And remember what that involves. That involves essentially taking the gradient, right, and setting it equal to the 0 vector. Remember, that's 0, 0. Or finding where it does not exist, right? Where either partial derivative may not exist. So that will give you the critical points, right? And there might only be one critical point. There might be several. There might be no critical points. And if there's no critical points, then there's no relative maximum or minimum points. Okay, so once you have the critical points, once you have a list of your critical points, however many there are, obviously if there's none, you're done. Then the answer is there are no relative maximum or minimum points. But let's say you have one critical point, right? So then how do we know whether we get a maximum or a minimum, or neither? So if you remember, in your Calc 1 days, you would use a test, right? You would use either the first derivative test, All right, derivative b. Or the second derivative test. You could use either. They both tell you the same information. Right? The first derivative test would always work. It would always tell you whether you have a maximum or minimum. The second derivative test usually works. However, there was a situation where it doesn't work, and then you just have to go back and use the first derivative test, right? Yeah, so that's nice because that's what you did in Calc 1. And roughly speaking, here's what you did in Calc 1 when you use the first derivative test. You have your critical number, right? And here it's going to be a critical point, so you have an x0 and a y0. But in Calc 1, you just had a critical number, say x0. And you make a sign chart for the first derivative. If the first derivative, let's say to the left of x0, let's say it was negative here. And then to the right of x0, let's say the derivative changed to positive. If that's the case, then you know you have a relative minimum. Because remember, when the first derivative is negative, you're decreasing. And when the first derivative is positive, you're increasing. And at x0, that's exactly where it changes, from decreasing to increasing. And that tells you you have a minimum. Right? Or, you know, if you reverse it, and you go from a positive derivative to a negative derivative, now you know that you have a relative maximum, right? And, you know, if the sign does not change, if it goes from a negative to negative or positive to positive, then you have neither a minimum nor a maximum. Okay, so that was the first derivative test from Calc 1. Hopefully you remember it, right? The second derivative test, you know, if you can take the second derivative, it's usually easier because what you do is you find your critical number and you just plug it into the second derivative. Right? And when you plug it into the second derivative, right, if you have a positive second derivative, then you know you have a minimum. Why is that? So remember what second derivative means. It means concavity. It means you're concave up. Right? And if you're concave up at your critical number, then you know it's a minimum there, right? If you're concave down, right, if the second derivative is negative at your critical number, then you know you have a maximum, right? So concave up, right, minimum, concave down, maximum, right? Night and day, very, very clear, right? But what happens if the second derivative equals 0 at your critical number? Then we have no idea. Right? You don't say it's neither. That's not necessarily true. It could be neither, but it could also be a maximum or a minimum. So when the second derivative equals 0, that's when the second derivative test just doesn't work, and you have to go back and use the first derivative test. Okay. So that's all from Calc 1. Unfortunately, Calc 2, because right, it's not a critical number anymore, it's a critical point. And because you have a surface, not just a curve, right? You have a surface in space. It's not just a curve. It becomes a little bit more complicated. And in particular, there is no first derivative test. So all this first derivative test business, that only works in Calc 1. So in Calc 3, we only have one test, and that's the second derivative test. Right, think about it this way, right? Remember, in Calc 3 now, we have a critical point somewhere in the xy plane. So let's say this is our critical point. Right? What would the first derivative test mean? Well, you look to the left and to the right. If it's positive here and negative here, that doesn't tell you anything anymore, right? Because it's not just left or right, right? It's up and down. It's along this direction, or this direction, or this direction. Right? So you can't possibly check all these directions, where it's negative, where it's positive. That'll just take you forever. Right? In Calc 1, there's only two directions, left and right. Right? It's one-dimensional. But in Calc 3, it's now two-dimensional. You don't just have left and right anymore. You have up and down, diagonal, all these directions, and it's hopeless, right? So there you go. There is no first derivative test anymore. There's only a second derivative test. Okay. And here it is. Okay, yep, so again, this is from the book, and this is the second partial derivative test, right? Yeah, so it's, remember, we're in Calc 3. It's not second derivative anymore. It's second partial derivative. I don't know why they said that. So second partials test, right? You have a continuous function f whose second partial derivatives on some open region for which the first derivatives are 0. Right. In other words, the gradient of f at the point AB, right, at the critical point is 0, right? So yeah, this point AB is a critical point. This is now a critical point, but only because the gradient is 0, right? This won't work exactly if the gradient does not exist, which is why you're not going to see that. Pretty much not at all. Not in this, not in the homework here, right? Okay, so we have a critical point. Now we want to test, is it a relative maximum or a relative minimum? Okay, so here is where it gets a little complicated, right? You cannot just take the second derivative and figure out whether it's positive or negative. You have to look at this number here. This is what they call D. Right, so D is just going to be a number, and it's this combination of partial derivatives. If you like, you can also take the determinant of this matrix here. So you have the fxx, fxy, fyx, which is the same thing as fxy. So maybe I'll just write down fxy. And then fyy. So if you take the determinant, you get this quantity here. Okay, so that's how I remembered it. In general, you get something called the Hessian, if I can spell it, Hessian. So this is effectively the Hessian determinant, or the Hessian matrix in general. But we're not going to need that here. As long as you remember what D is, you'll be fine, right? So you just multiply the diagonal, fxx times fxy, minus fxy times fxy squared, right? All right. So in order for the graph of this function to have a maximum or minimum, D has to be positive. So if D is positive, right, then you're guaranteed to have either a relative minimum or a maximum. Okay, so let's suppose D is positive. How do we know if it's a minimum or maximum? Now we use the second derivative test, right? We take the second partial derivative, let's just say with respect to x, plug in the critical number, the critical point, AB, and, right, so now it's just the usual second derivative test, right? If it's a negative number, that means it's going to be concave down. I'm going the other way, right? Let's say it's a positive number. If the second derivative is positive, it's concave up, which means you have a minimum, right? Or if the second derivative is a negative number, that means it's concave down, and that means this is a maximum. Okay? So, so that part is exactly the same. That part is exactly the same as in Calc 1. Right. But now there's a third possibility, right? This is possibility 1, possibility 2, but there's a third possibility. Before we even get to the second derivative, what happens if D is negative? So if D is negative, it turns out you don't have a maximum and you don't have a minimum. Here's what you have. Yeah, I was not going to try to draw this because I cannot possibly draw this well here. You get essentially this point right here, right? This is called a saddle point. Okay, and it's not a minimum, it's not a maximum, right? If you look along one of these curves, like this curve right here, this red curve here, it looks like you have a maximum, right? So you might say, well, then it's a maximum. However, if you look along this curve, right, this blue curve here, now it looks like you're at a minimum. So it just depends on your perspective, right? If you're looking on the YZ trace, it's going to be a minimum. If you're looking on the XZ trace, it's a maximum. So, of course, we give up and we say it's, right, this is neither a minimum nor maximum. Yeah, I should say nor a maximum. Okay, right. Instead, we just call it a saddle point. So, right, if D is negative, then the point, well, let's be specific here, right? We say the function, or the graph of the function, has a saddle point at the critical point, at the point AB, right? Okay. So there you go. There's three possibilities, right? If D is positive, right, then the function either has a relative minimum, right, at the critical point, or a maximum at the critical point, AB. And again, which is which? You look at the second derivative, right? It could be the second derivative with respect to x, or it could be the second derivative with respect to y. So you could use the y's here instead. What you don't want to do, however, is use the mixed partial. You don't want to do fxy or fx or fyx, because that could give you the wrong answer, actually. So just to be consistent, I'm going to use the x partials, but you can just as easily use the y partials, right? And maybe I should explain that. That has to do with D, right? So remember, D is this construction here. It's fxx times fyy minus fxy squared, right? And if this is positive, right, what it tells you is that fxx times fyy is greater than fxy squared. But remember, fxy squared is already positive. So it means the product, right, fxx times fyy has to be positive, right? So that can happen either where they're both positive, right, or they're both negative. So that's why you can use either the x second partial derivative or the y second partial derivative, right? But don't use the fxy, because that could be positive or negative, and that will not tell you whether you have a minimum or maximum. Okay, so that's why you can use the y partials instead. In any event, right, when D is negative, you get a saddle point. And just like in Calc 1, right, there is an unfortunate fourth possibility here if D is 0. If D is 0, just like when the second derivative was 0 in Calc 1, then this doesn't tell you anything, right? This is inconclusive. Sorry, inconclusive. So what happens then? Well, in Calc 1, you would just go back and use the first derivative test. But remember, in Calc 3 now, there is no first derivative test. So now we really are stuck here. We really have no idea whether this is a maximum or a minimum. Okay, so that's really bad news. What can you do? Well, you can, use a graphing utility, use a graphing software, and graph the function. And then you can tell, based on the graph, whether you have a minimum, maximum, or a saddle point. But yeah, when D is 0, it doesn't mean you have a saddle point. It doesn't mean you have a minimum. It doesn't mean you have a maximum. It could be any one of those three. It could be any one of those. It could be a minimum, it could be a maximum, or it could be a saddle point. So those are the only three possibilities. But when D is 0, there's no way to tell which it is. At least, right, not based on just this information. You would have to base it on some other information, like the graph. If you can look at the surface, of the graph, then that might help. But unfortunately, we don't have a fallback. We don't have a first derivative test to fall back on here, right? So yeah, so that's very bad news. And to be fair, this doesn't happen very often. And it's not going to happen in the Homer, right? It's not going to say when D is 0, you know, if D is 0, then what can you, right? You basically just say we have no idea, and you leave it at that. Yeah. Well, here's what you can say, right? If D is 0, right, then you would say that the point AB, the critical point, is a degenerate critical point. Right. And if it's a degenerate critical point, that means we really have no idea whether the critical point gives you a minimum, a maximum, or neither. Or a saddle point, I should say. Right. So here, neither means saddle point. Right. In Calc 1, I guess we called it an inflection point. But don't do that here, right? This is a saddle point, not an inflection point. So just be aware of that. Yeah, so if you do see a degenerate critical point in the homework, my apologies, but I did not intend for that to be part of the homework. Because it's much more difficult to figure out whether it's a minimum, maximum, or neither. Okay, so we have our function, f of xy. It's 3x squared minus 8xy plus 2y cubed, right? And the question is to find any points, right, xy, at which f has a relative maximum or minimum. So we're looking for relative maximums, right? Those are your peaks. Relative minimums, those are your valleys. Okay, so remember the process. First step is to find the critical points. So what do we need? We need the derivative. Right? We set the derivative equal to 0. In this case, the derivative is the gradient. And it's just the components are the partial derivatives. So we get 6x minus 8y for the first component, and then we're going to get negative 8x plus 6y squared for the second component. So where does that equal 0? Well, you get your system of two equations, you solve that system, right? And you get your critical points. So how do we solve this system here? First thing to note is that this is not a linear system, right? That y squared kind of ruins everything. However, you've solved nonlinear systems before as well. So we should be able to do that here. So just substitution, right? Just use substitution. So how about if I solve for x? Or let's solve for y. Right? So 8 times y is equal to 6 times x. And then y is going to be 6 over 8 times x, which is also 3/4 times x, 3 over 4 times x, right? And so I can plug that into this y here, and I get negative 8x plus 6 times, well, y is 3 over 4 times x, but don't forget you have to square that. And that still equals 0. All right, so 3/4 squared is going to be 9 over 16, right, times x squared. And let's see, 6 over 16 is 3 over 8. And 3 times 9 is 27, so 27 over 8 times x squared. Ouch. So we get a quadratic equation, just not a very simple one here. So why don't I multiply by 8, right? I get 27x squared minus 64x equals 0. Okay, so we factor out an x, and we get 27x minus 64. So we get two solutions. One of them is just x equals 0. And the other is this rather unpleasant 64 over 27. I don't think we can simplify that. Okay. So yeah. So what does that mean for y? Well, remember y is just 3/4 times x. So 3/4 of 0, oops, sorry, 3/4 of 0 is still 0. And then, let's see, if I multiply this by 3/4, I think I get something over 9, 16/9, I think. So I hope that's it. So, yeah, so we get 2 critical points here. So 2 critical points. Right. 0, 0. And 64/27, 16/9. Right, I never said they have to be nice numbers. They don't have to be nice numbers here. Okay, so now what? Well, now I'm kind of running out of space, so give me a second and I'll free some space up here. Okay, now what? So now we have our 2 critical points, right? We can have one minimum, one maximum. We can have both maximums, both minimums, or one could be a saddle point, or they could both be saddle points, right? So how do we know whether we have a maximum or minimum now? Right? So we just use our test. In this case, all we have is the second partial derivative test, right? So that's what we need to do, right? So let's calculate d. Well, we need, okay, so we have the first partial derivatives. Let me just copy those down here. So fx is 6x minus 8y, and fy is negative 8x plus 6y squared. So now we need the second partial derivatives. So fxx, that's just 6. fyy is 12y, right? And fxy or fyx, you can check either of them. Either of them will give you negative 8. Okay, right, so what's my d going to be? D is going to be fxx times fyy minus fxy squared. So we get 6 times negative 8 minus 12y squared. So that's negative 48 minus 144 y squared. So evidently, right, this depends on x and y, although in this case it just depends on y. So let's start with 0, 0, because that's an easy one. If you plug in y equals 0, you just get negative 48, which is negative. And remember, when d is negative, you don't have to bother with anything else, right? This tells me that f has a saddle point, right, at 0, 0. So 0, 0 is a critical number, and it turns out to be a saddle point, right? Okay, so now let's look at the other critical point. The other critical point was this awful 64/27, 16/9. So let's see what happens when we plug those in. We still get negative 48, but now we get minus 144 times, let's see, y is 16/9 squared, right? So yeah, just use your calculator. I get negative something like 45/28/9. Actually, I didn't even need a calculator for this, right? You have a negative minus another positive, right? So 2 negatives. You add a negative and a negative, you know it's negative, right? So since it's negative, it's also a saddle point. So we get 2 saddle points, right? So f also has a saddle point, right, at the point 64/27, 16/9. Yep. So both critical numbers turned out to be saddle points here. Again, that may or may not happen in other problems, but that's what happens in this example here. So 2 saddle points. Right. Unless I made a mistake, which is entirely possible, you know, maybe we should go through this a little more carefully, but I think I did all the algebra correctly here. Might have messed up the arithmetic, but yeah, I think that's it. All right, so we'll go with that. Okay, so we'll do another example. So here we have g of xy, and it's just this function, 1/2 x squared plus 3y cubed plus 9y squared minus 3xy plus 9y minus 9x. Yeah. And the question is the same. Find any relative maximum or minimum points, right? So the book uses the word extrema. Find any extrema here, right? So we go through the same process that we did earlier, right? The first step is, as always, to find the critical points, if it has any. Boy, if it doesn't have any critical points, then we're done. Then it doesn't have any maximums or minimums, right? So, so take the gradient and set it equal to 0. So the gradient is, let's see, x minus 3y minus 9. So that's the first component. The second component will be 27y squared plus 18y minus 3x plus 9. And remember, that has to equal 0, 0. And notice the gradient exists everywhere. So the issue of where do the partial derivatives not exist, again, not an issue for 95% of these examples here, right? Right. So again, now we just have to solve the system of equations. And let me add the 9 to both sides. So x minus 3y equals 9, right? And, well, here you get a negative, but that's fine. So 27y squared plus 18y minus 3x equals negative 9. Again, this is a nonlinear system because of the y squared. But substitution just works fine, right? So I think I'll solve for x this time. It looks easier. X is just going to be 3y plus 9. And now we can plug that in here, right? So for the second equation, you still have 27y squared plus 18y minus 3 times, well, 3y plus 9 equals negative 9. So now we just solve for y instead of x. Not much different. Okay, so 27y squared, and then 18y minus 9y is 9y. And then if I add 27 to both sides, or actually, I want to add the 9 to both sides, right? I want this is a quadratic equation, right? So, so 27 minus 9 is 18, so negative 27 plus 9 is negative 18. So you can divide by 9, and we get 3y squared plus y minus 2 equals 0. And so this equation is not quite as simple. However, I'm guessing that we can just factor it. If you prefer, just use the quadratic formula. So I think the 2 goes here, the 1 goes here, and 3 minus 2 is 1, right? So I think it's got to be this, which means y is either 2/3 or negative 1. Okay. And so what's x going to be? Remember, x was 3y plus 9. So I'll do that up here, right? If y is 2/3, then x is just going to be 3 times 2/3 plus 9. So 2 plus 9 is 11. And if y is negative 1, then x is 9 minus 3 is 6. So, yeah, so x equals 6 here, and x equals 11 here. So, yep, once again, we get two critical numbers, 11 2/3 and 6 negative 1. Okay, now I know I made a mistake. I definitely made a mistake here. Oh, probably a really dumb one. And I'm sure some of you are screaming at me like, oh no, it's not this. So what did I do wrong? This is fine. Oh, 3 times 3 is 9, not 27. There you go. All right, so give me 1 minute and I'm just going to fix everything here. Okay, so I changed all those 27s to 9s. And let me just make sure I didn't make any other mistakes here. 18y, yep, minus 3x. So I think that's it. Yep. All right, well, here's the new quadratic equation. And we can divide by 9, of course. So y squared plus y minus 2 equals 0. And that's even easier. So yeah, one of them is 2. And they have to add to a positive one, so 2 minus 1 is 1, right? Yep, so there you go. Y is either 1 or negative 2. And that means either x, right? So if y is 1, 3 plus 9 is 12. And if y is negative 2, we get negative 6 plus 9 is 3. Yep, so still 2 critical points. So I'm sorry about that. Look, we all make mistakes, right? I'm glad I caught it before, like I did the whole thing. So here's one critical point. It's 12, 1. Remember the x comes first. And then 3, negative 2. So these are the 2 critical points. Okay. But now we have to test them to see whether we get a maximum, a minimum, or a saddle point. And for that, we just go back to our second derivative test, right? So, yep, so let's take the second partial derivatives here. Let's write down the first partial derivatives. Gx and gy. Boy, that 27y squared. It's 9y squared plus 18y minus 3x plus 9. All right, so now for the second derivatives. The second derivative of g with respect to x, then x, that's just 1. Let's do the mixed partial. If we take the x partial and then take the partial with respect to y, we get negative 3. And that would be the same thing if you did gyx, right? And then the second derivative of y with respect to y, and then y again, I think we get 18y plus 18, right? Or if you like, 18 times y plus 1. All right, so before we take the second partial derivatives, we need d. And d, remember, was, oops, sorry, not x anymore, not f anymore, but g. So gxx times gyy minus gxy squared. And so we get 1 times 18 times y plus 1 minus negative 3 squared. Well, that's just 18y plus 18 minus 9. So 18y plus 9. Make sense? All right, so that's our d. Again, it happens to just depend on y. But in general, it could depend on x or y, or both. All right. So now let's take the first critical point where y is 1. So that's 18 plus 9, which is 27. So that's d is positive here, right? And remember, if d is positive, it's not a saddle point. It's a maximum or minimum. Which is it? So now you go back to the first derivative. I'm sorry, not the first derivative. The second derivative with respect to x and then x. gxx, right? And that turns out to be 1, which is always positive. So remember, when the second derivative is positive, it's concave up. And that tells me that we have a minimum, right, at the point 12, 1. Right? A relative minimum, but if I just write minimum, that we mean relative minimum. Right? Okay. Now we have one more critical point, 3, negative 2. Right? So now y is negative 2. So d is going to be negative 36 plus 9, which I think is negative 27, which means this is negative, right? Which means we have a saddle point. So, yeah, right. So g of xy has a saddle point at 3, negative 2. Okay, so one minimum and one saddle point. Right, so that's the procedure, and you know the ones in the book should not be that much more difficult than these, but that's the basic idea here, right? Find the critical points, and then use the second derivative test, the second partial derivative test, you know, to figure out whether you have a minimum, maximum, saddle point. And again, hopefully you don't run into problems with this d equals 0 down here, right? Remember, that's when you get a degenerate critical point. And we don't want those because there's not much we can do to figure those out, right? So yeah, they're either not going to turn up in the homework, or if they do, then they'll tell you what to do to be able to determine which it is, which of the three it is, minimum, maximum, saddle point. Okay, so our next example is a little bit different, right? Here we want to find the absolute maximum and minimum values, right? Absolute max and min of the function f of xy. It's just the function x squared plus xy on this region here. So it's the set of points where the absolute value of x is less than or equal to 2, and the absolute value of y is less than or equal to 1. All right, so in fact, right, this is a continuous function, and this is a closed and bounded region. Closed and bounded region. So we are guaranteed to have both a maximum and a minimum. So whatever your answer is, you cannot say there is no maximum and minimum, or there is no maximum or minimum. There's got to be one of each, one maximum, one minimum, right? Okay, so now how do you find it, right? So basically the procedure is kind of similar to Calc 1. The first step is to find, right, so find the critical points. Find any critical points, right, on the region R. Okay, so what is this region R? Maybe we should graph it here. So here's the x-axis, right? Here's the y-axis, right? So here's 1, 2, 3, negative 1, negative 2, negative 3, 1, and so on, right? So if x is less than 2, right, it's this region here. And if it's greater than negative 2, right, it stops here. Y is between negative 1 and 1. So we just get this rectangle, right? It's just this rectangle. It's a closed rectangle. So we have to consider everything inside that region R. Right? But this is the region that we call R. So R could be for rectangle in this case, but typically R is region, and it doesn't have to be a rectangle, right? It could be a disk, it could be part of a parabola, it could be a whole bunch of things. All right, so this is our region, right? So find any critical points on that region. If you get a critical point, let's say out here, right? That's not in the region, so x might be 1.5 and y might be negative 3 or negative 4 rather, right? This is not in the region, right? Y is not between negative 1 and 1. So it may be a critical point, but we're not going to consider it. So the important thing is only the critical points that are on that region, right? Either on the region or on the boundary of it, right? So yeah, we have to also consider the boundary, the actual rectangle here. So I'll draw that in yellow just to distinguish from the purple, which is on the inside, right? All right, so how do we find the critical points? The usual way. Take the derivative, or in this case the gradient, and set it equal to 0. So the gradient, 2x plus y, and then just x. Right? So there you go. If you set the first component equal to 0, you get 2x plus y equals 0. If you set the second component equals 0, you get x equals 0. But if x is 0, then y is 0. Right? So there is only one critical point. It's 0, 0. And that's the origin. That's right here in the middle. Okay. So the second thing to do is to evaluate evaluate f at any critical point. B, where AB is a critical point. Right? Critical point. Right. So yeah, just plug in 0, 0 into f, and you get 0 squared plus 0 times 0. You just get 0. Okay. So hold on to that, right? We have no idea whether this is a minimum or a maximum, or neither, right? Because we're not done yet, right? Finding the critical points and plugging them into the original function just gives us the z value, right? So in other words, z equals 0, right, at 0, 0. Okay. So the next step, and this is going to be the tricky part, right, is to evaluate the function f, right, at x0, y0 for all points x0, y0 on the boundary of R. The boundary of the region, right? What is the boundary of the region? It's this yellow rectangle, right? This yellow rectangle. Right. And we have to evaluate the function at all of these points. Now that's a lot of points, right? In fact, it's an infinite number of those points there. So this looks like a really impossible task. Okay. On the other hand, it's really not that bad, and here's why. So let me just copy down the function again. This is x squared plus xy, right? Okay. So this is a rectangle. Of course, what do we know about a rectangle? It has 4 sides, right? So let's just give these names. You can call it top, bottom, right, and left. I'm just going to call them 1, 2, 3, and 4. Okay. So the top part of the rectangle is just a horizontal line, right? And it's just y equals 1. Right? So for that part of the rectangle, region 1, y is 1. So what's f of x going to be? Well, if you replace y with 1, you get x squared plus x, right? Which is just a function of x, right? So if we take the derivative and set it equal to 0, what do we get? We get x equals negative 1/2, right? And y equals 1. So now we just have to plug in that point, negative 1/2, 1, into the function. And if we do that, what do we get? We get 1/4 minus 1/2. Right? 1/4 minus 1/2, just double checking. So that's negative 1/4. Right. Again, hang on to that thought. We'll come back to that later. Right? Let's go on to the second region, which is the right part of the rectangle here. And this is just x equals 2. Okay, so for region 2 here, or for line 2, x equals 2, basically just tells us that we have 2 squared is 4. Oh, sorry, this is a y now. Plus 2y, right? And when you take the derivative of that with respect to y now, you just get 2. But 2 is not 0, so we don't get any other critical points on that line. So that's nice, right? Let's go to region 3, where y is negative 1. Okay, so here I think we just get x squared minus x. And then when you take that derivative, you get 2x minus 1 equals 0. So x is positive 1/2. So now we plug in that point, positive 1/2, negative 1, into the function. And we get 1/4 minus 1/2, right? 1/4 minus 1/2. I'm just making sure. So that's still negative 1/4. Okay, so nothing new, but hang on to that. And then finally, region 4 here, that's the left part of the graph. That's x equals, so region 3, oh, sorry, wrong color. Region 3 was just y equals negative 1. And region 4 here is x equals negative 2. Okay, so for region 4, x equals negative 2. I think we get the same thing, right? We get 4 minus 2y now, right? But the derivative of that is never 0. It's just negative 2, right? So never equal to 0. So that's it, right? But here's the one thing we did not look at carefully. The 4 corners. These points here. So those are also on the boundary. So we have to evaluate f at the 4 corners. Right. So remember the corners 2, 1. Oops, sorry. 2, 1. Going clockwise, 2, 1, we get to 2, negative 1. And then negative 2, 1. Or sorry, negative 2, negative 1. Either way, as long as you have all 4 of them. And then negative 2, 1. Okay, so plug those in and you're going to get what? You're going to get 4 plus 2 is 6. Here you get 4 minus 2 is 2. Here we get 4, let's see, 4 plus 2, that's also 6. And then we get 4 minus 2 is 2. So you put all these together, and don't forget the critical number at 0, 0, so we had that one as well. 0, 0, that just gave us 0. Sorry, 0. All right then. So I think we hit all the points on the boundary that are on the rectangle, including the 4 corners. And so what we have is a bunch of z-values. What are the z-values we have? Well, we have 0, right? So the z-values here. We have 0, we have a 2, we have a 6, and we also have negative 1/4. So out of all these values, the biggest will be the maximum, the smallest will be the minimum. So the absolute maximum, well, I hope you know which number is biggest. All right, that would be the 6. 6 is the absolute maximum. And the absolute minimum, that better be the only one that's negative is the 1/4, right? So negative 1/4 is the absolute minimum. And those are the max, right? This is the maximum z value. right? So the maximum z-value, and then this is the minimum z-value. So that does it. That answers that question. Right, find the absolute maximum or minimum of a function on a closed and bounded region. And so, right, there's a theorem that says if you have a continuous function, right, on a closed and bounded region, you are guaranteed to have a maximum and a minimum. We have a maximum at 6, a maximum of 6 and a maximum and a minimum of -1/4. Okay. Now keep in mind that the maximum value occurs at 2 different points, right? It occurs at these corners up here. I should do them in red, right? What were they? Yeah, 2, 1 and -2, -1. So the upper right corner here is where you have the maximum of 6, and the lower left corner, you also have the same maximum value of 6. The minimum of -1/4, that also occurred at 2 different points. Can I use blue for that? -1/2, 1. So that would be right about here, at this point here. And so that was where you had -1/4. And then +1/2, -1 was right about here. So that also has a value of -1/4. So yeah, 2 points where you attain the minimum value, and 2 points where you would attain the maximum value. So the 0 and the 2, right, those are neither maximums nor minimums, right? Oh, they might be relative maximum or minimums, but that wasn't the question, right? The question was to find the absolute maximum or minimums. So there you go, right? So yeah, unfortunately, these types of problems where you're finding the absolute maximum or minimum, you have to look at the boundary, right? And in this case, that was a complicated thing. The boundary consists of these 4 line segments. So we had to look at all 4 line segments and find the critical numbers there, right? That was the critical points, right? Critical points on the boundary. And we also had to look at the 4 corners separately. Sorry, I made a mess there, but those are the 4 corners. So yeah, not an easy problem because the boundary was, divided into these 4 parts plus the 4 corners. Right. Yeah. In Calc 1, right, you have an interval, right, from A to B, a closed interval. So in other words, you have your left-hand endpoint and your right-hand endpoint, A and B. So the boundary was just those 2 points. So all you had to do was plug in the A and the B into the function to determine if that's where you have a maximum or minimum, absolute maximum or minimum value. So yeah, in Calc 1, the boundary was really just 2 numbers, A and B. But in this problem, the boundary was the entire rectangle, right? The entire yellow rectangle here. So yeah, not fun. Not fun. But that's what you have to do in order to find the maximum and minimum. In fact, the maximum and minimum occurred on the boundary, right? It did not occur at a critical number in the middle here with the 0, 0, but in a different problem it may, right? You may get a maximum value or minimum value at a critical number, critical point, but not in this problem here. So yeah, and we didn't have to find the critical points here, but we didn't know that before we went into that, right? We only found that because we found a number bigger than 0 and a number less than 0. So 0 did not give us a maximum or minimum. I better end it here, right? So don't get confused between relative maximum and minimums. Those are the peaks and valleys, and then the absolute maximum and minimums. And for that, we just wanted the values, the 6 and the -1/4. Right? They didn't ask us at what points they were, but if they wanted the points, right? Here are the points for the maximum, and then the -1/4. Those are these 2 points up here on the upper left. So that's where you have a maximum and minimum value, but here they wanted the absolute maximum and minimum values. So by values, we mean, z values here. Right. All right. Best of luck.